let's get started. It's a little early, but anyone who comes in late probably doesn't want to miss anything. So I normally do a lot of soft talks, and I like soft talks because I can say whatever I want, and no one can tell me it's wrong because it's really my opinion. I've done some things about how versus why, and it's funny that Matt Eminetti brought that up, but that's like really one of my things. We should know why we do things rather than knowing how. How is easy. You just go read Wikipedia, and it'll tell you how to do anything. So today, I want to actually invite you guys to my class, CS304, the Data Mining Exploration. And like any good class, we have objectives. And like any good professor, I'm just going to read what's on the slide. So we're going to explore the facets of machine learning. We're going to learn the ins, the outs, the whys, some of the hows. We're going to learn what it means to be a data scientist. Contrary to popular belief, data scientists actually have been around for a very long time. They were just called analysts back in the day, but now we have big data, so you have to have a data scientist to actually understand it. And we're also going to talk about practical applications of converse inductive integrals in the context of epsilon. Anyone ever dealt with this science before? So next, let's just do a review. Everybody here is good at math, right? So it's funny that this equation right here is a simplified form of, does anyone know? It's a support vector machine. But we'll talk about that later. And next up, we're actually going to talk about math, because everybody likes math. But before that, I want to give you some background. This is an introduction to machine learning. But not really, because I really hate that term. Machine learning is one of these things that we've invented to basically give an analyst something to do. So we're actually going to call it an introduction to data mining, because really that's all we're doing. We're looking at data we have, and we're trying to give the computer insight on how to deal with it. So let me actually get out of this. Let me mirror my desktop. Is there an easy way to do that? Is it control? Is it? Oh, well, we'll just do it this way. We'll mirror these displays. And what I want to do is actually show you something about my computer. What I want to do is show you that my computer is smarter than your computer, because I have taught my computer how to learn. And I wrote this simple little web app. And what it does is it says, I reload it, and it picks a random number. And I have thousands, I have actually literally 60,000 pictures of numbers. Single digit, they're 28 by 28. And my computer can actually look at those 28 by 28s, that's 700 and some pixels, and actually figure out what that number is. So as I do this, you'll notice it thinks it's a 1. It looks like a 1 to us. We're really good at this kind of stuff. This one's a 6. Let's see if we can find another one. 7, I was right. 0, I'm actually looking for one where it's wrong, because the crazy thing about this is that it's not perfect. There we go. The computer actually thought that this was an 8, but it's actually a 5, and you can look at that and you can actually infer that. So how do we actually teach our computers how to do this? How do we actually teach our computers how to learn? And this is actually weird. I posted on Twitter that I was giving a talk at a Ruby conference about machine learning. And I got DMs saying, really? Machine learning in Ruby? Yeah. I will preface this with one comment. We all like Ruby. We all understand Ruby. Sometimes you need to understand the concepts before you can run fast. And actually learning some of these concepts in Ruby and other languages like JavaScript will actually give you the insight you need and the intuition you need to actually understand this before you actually apply it. So yes, we are doing a machine learning talk in Ruby. So this talk is actually going to go wide. I didn't want to pick a topic and then go deep into that. I hate when at a conference where I don't actually know you guys. We're not all PhDs. I mean, how many PhDs are in here? Actually, there's no PhDs in here. So none of us are PhDs. We actually want to learn, we want to know about a whole bunch of things, and I don't really feel that in this 40 minutes or so that I'm going to actually dive deep into any particular topic, because really that's kind of boring. So what kind of problems can we solve with machine learning? Actually, there's a whole class of problems. So we're going to actually talk about, in this discussion, we're going to talk about clustering, where we're going to actually find like amount of things in a space. We're going to talk about, or actually grouping like items. We're going to talk about classification, like I showed you in that web thing, where we can actually figure out what something is. And we're going to talk about regressions. I'm not a statistician, and the word regress to me means to go back. So it's weird. Regressions are a weird term, but we're going to talk about regressions. Well, basically, we're going to talk about how to predict things with lines. So, but other problems you can solve with machine learning. There's a whole class of network security problems where you actually have these analytics packages that can actually look at network traffic, and over time, you can actually say that this is good or bad traffic. Email processing and spam detection, machine learning. There's actually a lot of prediction things you can do with machine learning as well. And next, we're going to talk about supervised versus unsupervised. I promise there is code, but I need to get some of these words out of the way so you can't say that I just chopped into something you had no idea about. So supervised versus unsupervised. With some machine learning algorithms, what you need to do is you need to feed it a very large number of examples so it can actually determine what's right or what's wrong, or what's a 1 and versus what's a 2. What I showed you before, the actual, this thing right here, I had to train it with 50,000 samples. And because I used Ruby, it actually took 3 days. If I would have used like Scala or Java or libsvm proper, it probably would have taken a few seconds. But this is not a dig on Ruby. So unsupervised machine learning language or machine learning techniques are things like clustering. Most clustering, they can actually just figure out that this group is here and this group is here, and you don't have to provide it any other data beforehand. So the nice people that get me here are Thunderbolt Labs. I actually own the company, so. But we're an awesome group of people. We have lots of awesome T-shirts. I saw someone wearing one yesterday. I appreciate that. Some people like to say that we're a boutique consultancy. I like to say that we are actually a business that likes to raise money before we do our products rather than going and getting VC money. So we have a lot of analytics things that we're doing for various companies, a lot of data mining. I'm Bryan Liles. Do not follow me on Twitter if you are easily offended, because I will offend you. And this is my company, Thunderbolt Labs. The reason I put this hashtag up here, or this Twitter @ thing up here, is because of this. We are sponsoring RubyConf this year. We are one of the gold sponsors. And the reason we are one of the gold sponsors is because of lack of diversity comments that actually came out after they announced their lineup, and we called bullshit on that. I've spoken at RubyConf, I've spoken at RailsConf. I've been asked to speak without submitting anything. These people are very, very inclusive, and we want to show our support by giving them our hard-earned dollars. So I also want to share this with you. I have two tickets to RubyConf that I will give up to 2 people in this room. All I want you to do is tweet it on Thunderbolt Labs why I should do it. And because our little thing is so long, it'll make it extra hard. And just let me know. And I'm not going to pay for your hotel, and I'm not going to pay for your flight, and I'm not going to buy you any food once you get there. I'm going to give you a ticket. That's the disclaimer. And I might not even talk to you once you get there. So, ticket only. So, back to machine learning, off my soapbox. Required knowledge. To do machine learning, you're going to have to know math. 1 + 1 is 2, unless it's 1 + 1 is 3. You're going to have to know better than that. You're actually going to have to know linear algebra. You're going to have to know some calculus. You're going to have to be able to draw stuff on a graph. But the best thing is there's Wikipedia, so you don't really have to know much math. You're going to have to read papers. I know this is not a closure conference, and I just can't actually give you a 10-minute talk and then say go read my poorly written paper afterwards. But you will have to read papers. A lot of these algorithms are made at these research universities where very, very smart people who get paid very, very little money to get their PhDs actually spend their careers writing these papers. And some of them are, actually, a few of them are pretty good. But a lot of them have the insights that you need for some of these techniques we're going to talk about. And you're going to need a lot of persistence. What things I'm going to talk about are not easy. They're not easy concepts. We are wired as humans. We are intuitive learners, and Your computer does not have intuition. There's actually no easy way to say, for your computer to actually go back to this image and say, hey, that's a 6. Hey, that's a 6. Hey, can do another 6. Aw, it's an 8. And I wrote this app in Sinatra. I could have wrote it in Rails, but I never get to use Sinatra, so I just wrote this in Sinatra. That's why there's no fancy stuff in there. All right, so let's talk about regression. So what are regressions? We're going to talk about linear regressions. And basically, a linear regression is we have a graph. We have data on the graph, like a scatter plot. And for simple linear regression, we have a line that we're basically trying to draw through the center of the data. So how does that look? Here's some math. Some of the more astute of you might have noticed, what is this right here?
Equation of a line.
That's right. There you go. It is an equation of a line. What is this bad boy? Do you know what this part is? Who said it?
Error.
All right, man. I didn't know. I thought this was all amateurs in here. But yes, it is the error. So really what you're trying to do is you're trying to draw a line that has the minimum amount of error. And I'll show you. I'll have a graph in a second about this. So for the more remedial of us, I actually have to go through this pretty slowly. So it is the slope of a line. We're basically as a line equation. And oops. So if I get out of here and I go to, everybody ever use the grapher inside of OSX? So, You never seen this before? I know everybody uses this. So we'll do it like this. So we basically get slope of a line, 5x plus 1. So basically we cross the y-intercept at 1, and we go over 1 and 5. So you see this is what our line looks like. That's exactly what we're doing. So basically I'm showing you here how someone just said, well, we'll just use fancy Greek symbols instead of what you learned in middle school. So another thing we're going to need here is data. And I found these data sets all over the internet. And really what I do is I just go look for machine learning data sets. This is actually a data set that maps the size of brains to the size of animals and mammals. I thought that was pretty interesting. So I said, what's the first thing I'm going to do with that? Well, I'm going to graph it. I'm using GNU plot here. Ruby has actually pretty good graphing things. If you want to use like JavaScript, you can use D3, or you can use Raphael, or you can use Canvas directly. But generating graphs with Ruby when you're not using web is almost a non-starter. So you have to use a tool like GNU plot. I love GNU plot. It's one of my favorite things. I've been using it for a very long time. And it makes it super simple to create graphs like this. So you'll see that most of the data is actually this data is fairly linear. And the reason I say it's fairly linear, because you can actually see that it does this. Like, we're going to draw a line that goes kind of like this through the data. And because we can draw a line through the data like that, we can actually predict other values. So if we can draw a line like kind of like this, I actually have a better image. If we can draw a line kind of like this, we can actually predict that if something has a brain weight of 15, it's probably going to weigh 100 pounds. I don't know where this data came from, actually. But up here, if we have a brain weight of, let's say, 26, that the body weight is going to be 160. Does anyone have a 26-pound brain? No, wow. Okay, so here's the error. The error is the distance between the slope, the line, and the actual point. And basically, we're going to minimize that to draw a line. That is not a real line. That is a drawing in Sketch. So going down and simplifying the error, I do not know why it's called the error. The error, for me, is something that is wrong. But someone named this thing the error, and that's what we're going to call it. So really, this Q is the sum of the errored squares for all these points on this line. So let's look at that. We can't have a Ruby conference without demos. Let's see. Can everybody see this? Is that nice and big? See what I did there? You should install Z if you're using Z shell. Or you should install Z if you're using Z shell. It's an amazing tool. So I'm going to do is go into this directory here, and I have lots of neat files in here. And because I'm running GNU plot, I can just pipe in, actually, let me cat what I'm going to do here. So what I'm doing is showing you on one screen in super big font how I drew that graph. Everyone here can read this. The most important line is the line before the end. It says plot this brain.csv using columns 2 and 3. And if I show you this brain.csv, you'll notice that columns 2 and 3 are just numbers. So what we want to do is, the cool thing about GNU plot is it does so much more than graphing. And I wanted to check myself before I actually got here on stage and show you that I could write code that did linear regressions in Ruby. So what I've done here is I actually wrote a version that works in GNU plot. GNU plot has this fit function, and I'll show you that code in a second. Blah, blah, blah. Lots of things going on here, but what we're looking at is for these final set of parameters. It's actually telling me what the mx plus b, it's actually telling me what the m is and what the b is. So remember 6.6 and 6.8. Those are our numbers, 6.6, 6.8. And the cool thing about this is because I use the plot function, I use GNU plot, I can actually go brain regression. Hopefully I don't have anything crazy up on here. I got a whole bunch of crazy stuff. Whoop, whoop. So this is what GNU plot did. It actually drew a line that minimized the errors, which is the distance between the line and the points, and it did all this nice stuff for us. So, but we don't want to use GNU plot. We actually want to use Ruby. So let me actually go back to this directory. I don't normally use Sublime Text, so forgive me for going really slow. We'll get rid of this. There we go. So same code, I just use this fit. So I was thinking, well, I can write this in Ruby. This is not hard. And even better, I can go to search on gist, because I'm sure someone else has already wrote it. So a lot of this code is cribbed with an attribution. So really what we're doing here is we're calculating we're trying to figure out what the y-intercept is, which is the b number, and we're trying to figure out what the slope number is, which is the m number. And I'm not going to go through this code because it's simple, pretty simple Ruby code, but the most important thing is that I'm actually going to do the same fitting thing that I did in GNU plot, but I'm going to do it with Ruby. So let's see how this actually works out. So let's run regression. I'm very horrible at naming. I saw John's naming talk yesterday, but I just call them regression with a 1 at the end. There you guys go. So you noticed before that we had these numbers that were 6.6 and 6.8. I can run this. This is deterministic code right here. So every time I run it, it's actually going to be the same. But you notice the numbers are very, very close. The reason why the numbers aren't the same, because I think that GNU plot is actually going further and actually having a level of confidence for this line. I just went and did basic math. But if I actually plot that in, 3, and I open Ruby, you'll notice that the line, actually, let me see if I can put these both on the same screen here. I do it like this. I'll do this one like this. The one on the right is with GNU plot, and the one on the left is with Ruby. The lines are pretty much the same. I mean, if you eyeball them, you will think they're the same. And once again, this is simple Ruby that actually anyone could write with the simple knowledge of regression. So, I know I'm not supposed to ask for any questions, but any questions? Should I go faster? Should I go slower?
What was that thing you just did to split the screen?
So here's a funny thing. I like talking about this kind of stuff, but I like talking about being very hacky better. You notice my shell is super customized. What this is actually Moom. And what Moom allows you to do is configure a key, because you can have a key combination, and I like moving things around. So I have it with spacebar, it makes it this way. I can make it go this way. I can make it go this way. I can quit it. I'm just kidding. That's not part of Moon. But it's very neat. So here's my favorite part of the talk, classification. How do we classify? There's binary classifications. where we can basically say, is something spam or is it ham, or spam or is it not? But there's linear classifications where you can actually plot things on a graph and actually try to classify them this way. And then there's something called support vector machines. I like support vector machines because it has a cool acronym. I can say I'm doing SVMs today. I made this with an SVM. Matter of fact, this was made with an SVM. And it's actually using libsvm. I didn't have to write all the hard code. But here's the best thing. What we're going to do here, and I'm going to explain this to you. See if I have. All right, I don't have a lot of slides for this. I actually have code. So what I'm going to do here is actually explain to you how support vector machines work. So this is what I call train Ruby. I write this kind of Ruby on the train. Notice that up top, I'm like, these are classes. I'm doing it the Ruby way. Notice at the bottom, I'm like, screw that. Train classes. So let me explain to you what this is. There's none of the magic. Actually, all this is doing is loading a data set into libsvm. So how libsvm works is this. We basically break down our images, or we break down whatever we're trying to classify into features. In the case of my images here, this picture is 28 by 28. So what I've basically done is now I have a linear array of 28 times 28. What the hell is that anyways? Did you know that? Really? Special mind over here. I'm going to need you to have stand next to me, so whenever I need to explain something, you can explain it in real words everyone can use. So we break it into 28, we break it into 784 array, and we basically say that every single pixel is a feature. And what we do is we tell libsvm that we have these features. So we have these features, and what libsvm does is it actually, when I train it with all the data, and I'm actually going to run this and show you how slow the trainer is. So what it will do is it'll actually start learning, and then after a while, it'll get to the point where I can actually say, well, what does this look like, and what does this look like based on the features? So we're chunking it up, giving it to the system, and then we're going to predict based on what we've known. And the cool thing about this is that these features don't have to be images. They could be anything. They could be components of a web transaction. They could be components of someone else. Like, I'm brown. How many other brown people are in there here? All right, I'll count you. So there's a few brown people in here today. So, I mean, we have components of being brown. I mean, we're beautiful. We're smart. Not opposed to anyone else, but these are classifications. So I could actually build a classifier that could actually classify us brown people. We all have two eyes and things like, well, most of us have two eyes. I don't want to offend. So that's what we're doing here. So we build this classifier, and I actually, you know what? There's a lot of math involved in here. I'm actually introducing terms. There is a very good reason why I'm not showing you equations for this kind of stuff. Because if you go to Wikipedia and you search for support vector machines, you're going to get this much math nomenclature. And then you're going to have to go figure out what this math nomenclature means. What I'm showing you is, hey, you can do some cool stuff. So here we have this, nope, I'm in the wrong directory. There we go. So we have this class 1. Once again, I'm horrible at naming things. So we have this class 1 thing, and what it's going to do is we're going to switch Ruby gems. We're going to switch Rubies. So the problem is that Ruby is, I have a whole bunch of Rubies on this machine, and I use RBM, so there we go. So what we've done is we have a file, and I'll show you this file in a second. Or no, I won't, because it's binary and you won't get anything out of it. But we have 60,000 images in here, and what we're doing is we have 60,000 labels, and we're basically saying that something that looks like this is an 8. Something that looks like this is a 5. And supposedly, if you do this enough number of times, what you can do now is say, well, I have enough samples. I can actually now start asking the model, what is this? What is this? And notice I didn't put how many samples I've trained here, but it wasn't very many. It's very, very slow. And I'm actually predicting 5,000. So I'm actually going through and predicting and figuring out how accurate my classifier is. We'll let that run. So next up is decision trees. You can imagine decision trees of huge list of if else, if else, if else, if else. I purposely did not talk about decision trees for the reason that there is a talk at RubyConf last year where this guy goes in for a whole hour on decision trees. And it didn't sour me on them, but I'm all decision treed out, and I would, if you really want to look at those, go look for that video. Is this thing done? Yes. So notice, since I gave my classifier not much time to train, it's not very accurate. I have a much more accurate one on the website. But notice that this last line here, or these last 3 lines, is that I had 5,000 in my prediction set, and I guessed only 66.08%. Is that correct, sir? Just making sure. And so this is the thing. So for classification, because it is supervised learning, you have to have a very large amount of data to train. But with Spam Assassin coming out well over a decade ago, this is exactly what they were doing. They were taking, so whenever you said this email is spam, this email is spam, or this email, and email 10 is spam. Even what you're doing right now in Google, whenever you're saying this email is spam, Google is actually taking that email, extracting out all the headers, who it came from, and creating features of that kind of stuff, and also what is in the message body, and it is actually building huge classifiers. I don't think they're using support vector machines, but they are definitely using something along the lines to do classification. Dun, dun, dun. All right. So, clustering. This is actually my favorite thing. Clustering. Finding groups of alike things. We're not going to talk about that yet. So I actually really do like this part of the talk. Even better, I made a website. So imagine you were an astronomer and you were looking at the sky and you were actually trying to figure out stars that were, when you look at the sky, it looks pretty flat. I mean, for thousands of years, we thought that the universe wrapped around the Earth, and we looked up, and we thought stars were stationary. But now we know that this is only kind of true, and if you watch Fox News, you probably don't believe this at all, but we know that space goes on for a long time. And then we know that things that we see stars that are next to each other, if we actually could go around, we could go 90 degrees around the axis, we would actually figure out that these stars are actually millions of light years apart. So what these scientists do is they actually can generate these listings. They can actually make these images, and basically based on, I guess, radio stuff. Sir, do you know what they do? So based on how far they know they are away, they can actually classify these things, and we can actually figure out what clusters or galaxies or whatever. So I was like, well, you know what? That doesn't sound very hard. So let me try this out. So let me show you this. It's actually, this is not Ruby. You don't run Ruby in a web browser. Or you can, but you don't run Ruby in a web browser. So I'm going to reload this page. And what it's doing here, I'm going to explain to you how it works in a second. But you notice that colors are weird. Please don't crash. I think it's crashing. I'm going to reload this web page. Oh, it did work, actually. I'm going to reload this web page. And notice that everything is in different colors. The clusters are not all the same colors and all this good stuff. But you notice, hey, what's going on? And you'll notice now that the clusters of stars are pretty much the same color. And I didn't tell the computer how to do that. What I did is I actually built up a cluster, and I told the computer to go cluster it for me. I said, Alfred, cluster the data. What does that do? No, I don't want to see what that website is. So let me explain to you what I'm doing here. So clustering. How do you tell a computer how to cluster things? Well, it's actually pretty simple. All these, there's actually 5,000 dots on this page. And there are actually 5,000 dots. And I'm going to show you how powerful D3 here is in a second. I'm going to go to this file, and I'm going to make the height a little bit less. So now all this should fit on the page. And I just told D3 to resize the page, and it has ranges, and it does all that stuff. So what I've told D3 to do is draw 5,000 dots. And then you see these bigger dots, like there's one here, and then there's one there, and there's one here. What those are, they're called centroids. And at a minimum, what I do is I just say, I think there's 14 clusters or 15 clusters on this page. I'm just guessing. Put 15 random dots on the page. And then what I want you to do is to draw, I want you to color all the little dots based on the color of the big dot that it's closest to. And then what I want you to do is move that big dot to the center of all the things that have that color. And then I want you to change the colors. So you notice as the dots were moving, I'm not really good at D3, so excuse my animations here and my transitions. But so we will call this train JavaScript. There's no test. And actually, yeah, my thing does crash the browser for some reason. But what it's doing is as it's moving, as we color, we measure again, and then we move, and then we measure again, and then we move, and then we measure again. And then what happens is at a certain point, based on there's nowhere to move. And the reason there's nowhere to move is because it's already in the center of all the dots that are around it. And then we have that as we say that it's converged, and we can guess what the groups are. So, the astute in here are going to notice that, hey, this is a green dot in the middle of a field, and it's not really the middle of a cluster. This thing right here that's sideways actually can never be clustered right. So here's the secret of k-means clustering. You don't run it one time, you probably run it 1,000 times. You notice this is very quick. And actually the reason that this took so long is because I put some timeouts in here so you could actually see the animation work. But really what we're going to do is we're going to run this 1,000 times, take all the data, and then we're going to give you brain.csv. And if I show you this, we're going to number all the clusters, and we're going to give you a statistical number. So we're going to give you line is the line before the end, and the standard deviation of the probability of you being in a certain group. And we can actually use that now to actually say, look up at the skies and determine what galaxy something's in. The reason I like to show this is because, first of all, it's in D3. Anyone here use D3? You should actually take a look at it. There's not much code here to actually draw this. And I draw it in a very stateful way. I don't actually say that this pixel is here. And actually my coordinates, let me show you my coordinates. This is actually the neat part. My coordinates, let's see, this is a clustering exercise. My coordinates aren't even in screen coordinate space. They're actually in whatever space, I don't know. My screen at home has 664,000 horizontal pixels, but my MacBook Pro here does not. So, but no, I'm using D3, and I'm actually drawing. Let's see, where's my index? So I'm actually using scaling inside of D3. And the funniest thing is that a month before last, I actually gave a talk in Wales on using D3, and I was really good at it then. But I haven't used it since, and I'm not so good at it anymore. So now I'm just basically scaling and doing some neat things and then doing some transitions and all that stuff. Notice there's no classes in here either. I actually went old school and wrote it all in functions. So, once again, I'm not here to teach you anything. I'm here to introduce you to things. Let's see, what time is it? All right, we're doing all right in time. So when I first wrote these slides, I was actually getting, I was feeling really good. And I was like, I'm going to show them a whole bunch of demos. But I actually forgot to make one for the Jaccard Coefficient. So I'm just going to talk about it. Imagine you're a teacher, and you are a college teacher for not a great school. You're a college teacher at a state school. And not just a state school, like a state school that you go into when you don't take Spanish in high school. So that state school. So, and you're an English teacher, and no one reads the books. Who here reads? I don't read. I read tech books. But people have to write papers, and there's going to be a lot of cribbing, a lot of cheating, and basically a lot of recycling of papers. What I can do with the Jaccard Coefficient is this. I can actually cluster documents based on scores. So what I can do is I can take all the papers, and this is actually how the software works. I can extract all the numbers out. I can calculate the relation of having all the papers that have the word Boston in them. And I can actually group those together, and I can actually generate scores around this. And I can actually, instead of having to look and actually read these papers, I can actually generate these scores around this and group papers. And if I run it on all the papers that are similar will have a similar score. And then I can actually go read those. But teachers don't really teach any days, so they probably don't care. I can group documents. We can detect plagiarism. Oh, I did this out of order. Oh, okay. So now we're not going to learn anything new from now on. I only have a few more minutes. It's me talking about doing this kind of stuff for real. There are tools out there. There's AI4R. You should go look this out. You can actually gem install AI4R. And how do you say that here? Well, AI4R. You can, So you can actually gem install this. A lot of the things that I talked about are implemented inside of AI4R because really you should not be writing your own machine learning algorithms. You don't do that. Matter of fact, if you can write machine learning algorithms, come talk to me. I might have a job for you. You can use something like JRuby. You can actually go have a look at JRuby. I think it's a very important project for Ruby in general. They have a couple sub-projects. They are really putting a lot of work into doing scientific computing in Ruby a real thing. The problem is that no scientists actually use JRuby, so it is progressing at a glacial pace, but I still think it's a worthy project. I didn't talk about JRuby. Everything I talked about so far, I've done in MRI. And the reason why is because I actually wanted to start it, and I didn't want to have you guys wait for JVM to spin up to actually do this. So JRuby is interesting. Once it actually gets moving, it's kind of fast. I mean, so Ruby, JRuby, every other programming language in the world. But it's interesting, though. It allows you to, and I know Mark Menard, if he hasn't talked about JRuby, he is going to talk about it. I don't hate it. I just don't like it very much. But there's a Apache project called Mahout. Apache project called Mahout. I'm pronouncing how I'm going to pronounce it. And actually, it has a lot of these things. It has a lot of machine learning things in there as well. They have great clustering stuff. Apache made this. This is an Apache project, and a lot of people are using this, but they don't have a lot of hooks to Ruby. But I just know there's an actual association machine learning stuff in there with JRuby. So, Rails on Ruby. So like I said, when I started this talk, I tweeted that I was going to at least talk about these topics in Ruby, and I got some not so nice responses, like, why would you do this? Ruby does not have fast math. There are projects that are based on BLAS, which are basically Fortran hooks. There's one called Matrix, which is actually part of JRuby. I can't install it on my Mac. I can install it on Linux, but it does not install on my Mac. And that's kind of a non-starter for Rubyists. I mean, a lot of us use Macs. So Ruby does not have fast math. It can add 1 + 1 pretty fast. I mean, that's good stuff. But Ruby does not have great matrix supports. So if you're trying to do a matrix and you want to have 1,000 by 1,000 and you want to do dot products of that, Ruby probably could do that okay. But if you want to do 100,000 by 100,000 or 100,000 by 50,000, Ruby is not going to do that very well. A lot of these libraries are based on Fortran code. Believe it or not, that is the secret for making everything fast. You write it in Fortran. But Ruby does not have fast math. Ruby does not have easy plotting. For showing you the clustering example, I had to write it in D3. There are projects coming out of JRuby that are going to try to solve this, but you can just take a step over the aisle and look at Python, and they have matplotlib, and it's super simple to use, and it's super nice. Ruby does not have an integrated environment. When you're going to have scientists, and not web developers, I'm actually not talking about web development at all. When you have scientists, people who wear lab coats to work, these people want an integrated environment. This is why things like MATLAB are so popular. But if you ever use MATLAB, while being popular, it's an awful piece of software. Whenever you want to require things in, you just put it in a directory, and then it suddenly is in your namespace. And MATLAB is not approachable in price, but you have Octave, which is free, but still, it's not great. And then when you want to expand out to more than one machine, you don't have any access to being able to expand out to more than one machine for your calculations. So you can move to tools like Mathematica. Matter of fact, I'll tell you what, I love Mathematica. I didn't think I would, but for an esoteric, like really crazy, like I'm a smart guy and I'm gonna write smart guy shit, this is the tool you want to use. If Dr. Evil wrote math code, he would use Mathematica. And as a matter of fact, I'm not going to even show you Mathematica because you should just download the demo. I don't remember how to use it right now. Yeah. But you know what? There is a Mathematica for us, our basic noobs. It's called the IPython Notebook. As Rubyists, you guys probably like Ruby. But as technologists, you should love cool software. You should go check out the IPython notebook, and I'm going to show you why. So I'm going to create a new notebook in Python. And this is kind of like Mathematica, if you've ever seen it. So what I can do, and this is a web page. So basically, it's like a web page IRB, or actually more, it's like a web page pry. So I can actually come in here, and I can assign some variables. A equals 5. And then I can run this block. And it says, hey, yeah. And if I go down here and I try to see what's in there, it says, hey, it's 5. I can go, but I don't have, I actually uninstalled it, and then I realized the install was like 240 megs, so I didn't want to download it on my phone. But it actually has support for doing graphs in line. People are working on animations. And whenever I close this and come back to it, it saves it. The IPython notebook is actually going to change how people do science. I truly agree with this. And the reason why is because not everybody can afford Mathematica. Even the Mathematica I have was very, very, very expensive. And for you to run it on multiple cores, it's crazy expensive. And IPython comes with these things called these workers. So you can actually create distributed apps with IPython just by launching a server on another machine. It's actually a great thing. So, moving on. Here's the last thing. I'm not going to dance, which is funny because I keynoted Ruby Nation, and I said I could do a talk on anything. And Nick Gauthier, I know I saw him. He's in here. There he is. He put up a lightning talk for, was it interpretive dance with code? Or just interpretive dance. It didn't happen. But what I really want my environment to do, I want it to let me dance. I want to be able to do whatever I want to do, and I want to be able to get it done in a very easy and fast fashion. And we just don't have that with Ruby. I actually wrote a longer blog post. I was not trying to be mean, and I don't think anyone took it as being mean, but it really did reflect on the sore state of Ruby for scientific computing, almost to the point where I will formally say, if you were doing scientific computing in Ruby, first of all, I do want to talk to you about it, but your time is probably better well spent in Python land or Java land or somewhere else. And that's not a bad thing. I think it's really nice to be able to learn this kind of things on Ruby. And if you guys really want to see my code, you want to see my train code, I can put it up on GitHub and you can come see my train code. I'm happy to share with you because it's easy. They're easy to learn concepts, but if you're serious about this, you're not doing it in Ruby. And truly, if you're serious about anything performance-wise, you're not doing it in Ruby. I mean, let's not kid ourselves. You can make things very fast in Ruby. How do you make something fast in Rails? You cache it. That's cheating. That's not actually serving things. So we use Ruby because we like Rails. We like expressiveness of Ruby. We like these kind of things. But when it comes to doing serious big boy stuff with math, we use something better. So moving forward, you want to learn more? You got to learn linear algebra. You got to learn it. No, I mean, it's nothing here. You got to learn it. You got to know. Coursera has some great courses on it. Yeah, you got to learn linear algebra. And unfortunately, if you want to learn how to do minimizing and you want to learn how to do real gradient descent and all that kind of stuff, you have to learn calculus. You got to learn it. You got to learn it. But you know, the good thing about this is that by the time that you're out of high school, you should know calculus. First couple years into college, if you choose to do that, you can get linear algebra. So these things are not very hard. You don't need to have passed your bachelor's to learn all this stuff. The Coursera machine learning class, I think you should at least view it. The gentleman who gives it is very, very smart. And if you look at machine learning papers, you're going to see Andrew, is it Ning? I asked somebody this last night, and they told me, but Andrew N., you're going to see his name cited all over the place. It's because he's wicked smart. But the problem is that the way that it's presented, it's not presented in the way that a normal person who is not really used to this kind of knowledge is going to learn much. But you should at least look at it. And you should look at Wikipedia. I mentioned this before. Let me mention this again. Wikipedia, SVM. There it is, support vector machines. Wikipedia is the greatest compendium of information about machine learning out there right now. Everything you want to know about many, many topics are on there. Like if you want to look up, this is not machine learning, but if you want to look at a Weibull distribution. Anyone here know what a Weibull is? What you use a Weibull for? Meantime, you actually calculate depth with a Weibull distribution. So in a population or with hardware, you can actually say mean time between failures, or people's lives go like this, but as you approach as you get older, the distribution graph will go like this. Reverse that, I'm actually doing it the way I would look at it. So like this, you would do the wave. So you got to use Wikipedia. Wikipedia is a great resource. But now if you want to get serious, find a data set. And I do go machine learning data sets, and there's thousands of data sets out there. The data set I use for the classification of numbers is the MNIST data set. I actually found the brain stuff just by doing a casual search. And then I found a whole bunch of other data sets. And then I found the Starfield stuff just by saying clustering data set. Find a data set. Find another language. Do whatever you do and profit. Or you come work with me and you'll be real profitable. But there's a lot of money to be made doing this stuff. And even, I'm telling you what's out there right now, there's some great things out there right now, but the space is still kind of young for people who are doing it outside of academia, and there's a lot of space for making a good amount of money. We haven't scratched the surface. This right here is a list of like a flow chart from the scikit-learning site. So this is basically machine learning in Python. They actually love it so much, they make it so you can just go pip install scikit-learn, and you can do everything I did here in like 10 seconds. But this is like a graph of our chart of showing you how you would progress and how you would figure out what you're going to use. Notice I didn't talk about any of the new cool stuff like deep learning or neural networks. Go look at Big ML. They're a really cool site. It's a website. Go look at Dundas. They're kind of like Big ML, but they're not as popular. Go look at Kaggle, especially their blog posts and their competitions they run. They have great data sets, and they have great insight. And you might want to go visit Python land if you want interpreted languages. Go look at Apache Mahout. And for my last slide, this is a new thing. It comes from Berkeley. It's called Spark. And basically, basically a better way of running distributed computing. There's something called Shark that actually does machine learning on top of this. You should actually look at this. It's pretty amazing. And that's it. Note one thing. Notice that I did a lot of talking about a lot of high-level things in, I don't know, 45, 50 minutes. This field is incredibly huge. You could have conferences on this stuff. So if you have any questions, I know I don't have time, but you have time for 2 questions. I promise you that I have no guarantee to answer them, but guy in the pink shirt at the top.
Does R have a place in this?
Oh, crap. So, yes, someone else asked me a question while I do this.
Where can we get your slides?
Where'd I get my slides?
Where can we get your slides?
I don't know. Where do you want them? So, R. So you want to do some R. So remember we were talking about clustering earlier? Yes, I found examples to back every Ruby example I wrote. And yes, I wrote a cluster. Well, I didn't write this. I refined this clustering algorithm and k-means clustering in R. And you know what? If you use something like RStudio, you get great graphical output. So yes, R, SAS, yes. Next question. Yes?
You mentioned at the beginning that when you did the classifier for numbers in Ruby, it was a long time, and I thought you were using libsvm.
So here, yes, I'll tell you why. And it's 3 letters, global interpreter lock, which means that basically I can only use 1 core. This thing has more than 1 core. So I wasn't able to do it. And it actually was like 100%, 100%, 100%. So the problem is that a lot of these algorithms, they're deeply threaded, but even with threads in Ruby, you're not getting over one core. And what's the answer from Ruby land? We'll run more than one, but you can't when it's a non-parallelizable algorithm. Pow. They're also not traps. I will put the code up in the slides. I will put those up too. I'll export in a PDF, and I'll make a new GitHub project. I think I know how to do that. And I will tweet that I did that. So it might be like 2 weeks. But I will do that for you guys. So thank you guys. It's been great.